So, continuing our story about the new definition of convolution, I basically already answered number 2 for you, which is that there's a condition we'd like this function to have. All we know now is that it actually does give you a value for each t. But because this is exactly this idea of taking a thermometer, G, it happens to be G check, no big deal, and sliding it progressively left and right, if we slide it a tiny bit left and right, this number should not change very much because similar thermometers should give similar results. In other words, this function should be continuous. Okay, that's a good thing because the compatibility condition I just wrote down, let's write it down one more time and be really explicit about it. U star new G, and then thinking of it as a distribution acting on phi, we'd like that to be U star old G acting on phi. By definition, this was U acting on, let me just get the checks right, phi star G check. Okay. We'd like that to be compatible with this guy. Okay. And so what is that? U on integral minus infinity to infinity phi of t, and then starring with g check. Well, I'll just leave the check in place because it's not that significant right now. We don't need to deal with it. And one thing here is just the way the letters have worked out. The dummy variable is now t, and the actual active variable is ta. And so u is really looking at a function of ta and acting as a distribution on that. And then here, this is integral minus infinity to infinity of this function, u on g check t, and then put just integrating that against v of t dt. Okay. So we don't know if these are equal. This wouldn't even make sense unless we have some idea that this is at least a locally integrable function, not something truly bizarre and random like it could be, really, as far as we know. So we want this to be at least nice enough to write down this integral at all. And then we want we definitely, basically, because we can't take any function and promote it to be a distribution. All we know, the only functions we know how to promote to be distributions are locally integrable ones. And we really want it to be continuous because we don't want these two thermometers to give different results. So those are two big things we want to prove. It's going to take us a lot of this handout to do that. Okay. So, so the first thing we could hope, maybe, okay, we have to do something. We have to add more to the definition of a distribution because we just don't have any condition that would possibly make this nice in any way. So why don't we just by fiat say, okay, we're only going to allow distributions where if you do this process with a test function, in other words, you take one particular shape of thermometer with one particular response function and then slide it left or right, that you get a continuous result, that the numbers you get vary continuously. Okay, so it's a typical thing in mathematics. It's not a horrible thing to do. If you've got a definition that you don't think is set in stone, and you have reason to believe that you can still play with, you can add to that definition. And if there's something you really want to be true, maybe we should just do it by fiat. Okay, so I'm going to call that condition A. And I've already given the game away a bit, which is too bad. Otherwise, punchline would be better. That this is not going to be the final condition. Okay, and that's going to say you have a linear function. And remember, when we say function, it's a pretty sophisticated idea of function. It's something that takes test functions themselves, functions of real numbers, and spits out a number. So the kind of thing we've been dealing with is a distribution. Okay, so far this is what I've been calling, quote, a distribution, because we haven't had to face up to this issue yet. Let's say it satisfies condition A, and this is some version of that u is a continuous function that eats test functions that are very similar to each other and produces similar real numbers. If and only if, where the number is if with two f's, nice abbreviation, for all test functions, g, say, or no, yeah, g. G and phi are all, there are test functions in this whole handout. They have slightly different roles, but they're just good letters for test functions for these purposes. The function, really this convolution function, but I'm just going to say take t, produce g check t with a little the translation parentheses, and then put it into u, and you're supposed to get a continuous function. Now, one drawback of this, anytime you put a condition on, there's really two crucial things to ask about. One is, what does it buy you? And we've already seen that this would buy us a lot. It buys us a lot of good stuff about how we want to represent our models, and maybe a good start on proving the convolution definitions are the same. But you also want to think about, is this easy to check in practice? And it's not clear if that's really easy to check in practice. Luckily, we're going to look at the fact that this definition is going to morph into other definitions. So we're not going to really look too much at how easy this is to check. But it's something to think about. That's the flip side to just defining everything to be true, because maybe you can't actually check that it's true. So in other words, just a slightly different way to say this is we would propose a tentative definition that a distribution, the honest-to-God real definition of a distribution, is a function that each test function gives real numbers. It has to be linear. We've seen many uses of that already, and we'd never throw that away. And that satisfies this condition, condition A. So that basically u star g is always continuous if g is a test function. Okay. So we certainly wouldn't want, even though I'm not going to go through like a process of checking this for all functions, we certainly would not want to even discuss this if it excludes our standard functions. And even though this isn't going to be the final definition of continuity for a distribution, it's going to bring up some great issues that go through the whole rest of the handout. Okay, so problem number 3 is just checking that this is not crazy. Okay, and so we'd like to check for like a delta function. Does this satisfy condition A? What about delta prime, or more generally an nth derivative of a delta function? And what about a function f considered as a distribution when you think of it as something that you integrate against? Okay, so part A is checking this for a delta function. Okay, this is really, really easy. T goes to, well, basically, in this case, we actually know that the definitions are equivalent, really. This is a little bit different from how I have it currently written out. So in other words, the new style convolution of delta with g of t, what does that new style convolution say? It says take delta and act on g check translated. Oh, but delta just says take that and evaluate it at 0. So that's g check of 0 minus t. Oh, but the check just takes the 0 away. Oh, surprise, surprise, g. Okay, this is another way to see why we need the check, because you're going to get a minus and you need to kill it. Okay, wait, that's just exactly delta star old of g. Okay, we knew that the delta function, when you convolve that with the test function, you just get the function itself. And that's certainly continuous. It's much more than continuous, which is actually a hint that maybe we can actually expect more than continuity for a convolution of a test function, or a distribution and a test function. But we're not going to jump the gun on that. Okay, so that was really pretty much tautological, basically because delta evaluates a function, and I'm not doing anything that's weird in terms of evaluating a function. Delta to the nth derivative of delta, very similar. We also have delta. Actually, you know what? I'm going to leave that to the handout. It's so similar. We will see situations where delta works and delta n doesn't work. One of our attempted conditions, one of our attempted definitions, it's exactly the derivatives that will screw up, but here it's really okay. The main thing I'll say is that it uses the fact that g to the n is continuous. Because when you convolve this guy with g, you're going to get this guy. And our test functions are infinitely differentiable. All those derivatives are continuous. Okay. Now, to look at a function f, that's very interesting. Okay. So remember that we know the whole motivation for this was that if you look back, if to really nail down all the details of this, you have to go back one video or one handout and see that the old definition, there's really sort of three definitions of convolution for functions. There's the standard integral definition, which we just rephrased it. We didn't really do anything. We just did some tiny manipulation to just rewrite it to get the new definition as applied to functions. And the old definition, when you have a function thought of as a distribution, this was actually to prove that this distribution version was the same as just the good old function version back from like Handout 1. That actually required a little work with Fubini and stuff like that. But we know that, and we know these guys are equal because we just rewrote it. And so these guys are the same. So if f is an ordinary locally integrable function, we know there's no distinction between the new and the old definitions. Okay, but one thing we have never shown about this is this kind of continuity statement. Okay, and that's well worth looking at. Okay, so we want to know that if f is integrable. At some point I should clarify that that's really means locally integrable. I just mean not a horrible function. I'm not assuming anything about its decay at infinity. So for example, the function 1 is totally, I'm saying, as integrable, which is not the usual use in mathematics, unfortunately. If f is integrable, so locally integrable, I guess you'd say, and g is a test function, then f star g is continuous. I guess we already know this, we've had a backdoor kind of proof of this, because we've looked at sort of derivatives of convolutions. But I want to lead us through a much more careful analysis of it, because it's going to be really, really important for this and much other stuff for the whole course to come. Okay, so here's what we're doing. We've got f, remember, and we're bracketing that, we're acting that with that on g check t. And I'd like to know much more about how these functions change. It's a family of functions here. So as t changes, I've got this family of functions. Now, it's not a particularly complicated family of functions. It's just migrating it to the left or right, just shifting it. But I'd like to know more about how to understand how those functions change. In particular, if two values of t are very close to each other, in what sense are the g check t's close to each other? And is that enough to make f acting on that nicely behaved? Okay, so it's a good excuse for introducing some nice notions, and I'm not going to go through all of this problem, but I'll introduce the first notion and then stop after a few more minutes. Okay, we are looking at g check of t, and I'd like to assert that those get closer, they converge to the function, say, g check t naught. I really need the parentheses, huh? I'm not going to put the parentheses around the g check. It's understood that I check it first and then I do the translation. So that's okay. Okay. I'd like to assert this as t goes to t naught just as numbers. So if the limit of a family of t's is t naught, then these guys go to this in what sense? Okay. So I'd like to assert that they go in a very important sense, which is called converging uniformly, and that is. So I'm not making an assertion here yet, but I'm just coming out with the definition of what we'd like to be able to say. For every epsilon greater than 0, very standard start for a continuity kind of statement, or a convergence kind of statement, sorry, there is a delta greater than 0 such that I compare the values of g check t, the translated function by translating by some movable amount, and then I'm going to have to evaluate that to make it more explicit. What do I mean? It's a function after all. And I'm going to compare that to what the sort of base case is going to be. So I really want to think of this as kind of untranslated. I translated it once and for all by t naught. Maybe that's this guy. And then I'm wiggling it by a bunch of values t that wiggle back and forth around t naught. And the key thing about this is that, so let me finish it. For all ta in R and all t, as long as they're close to t naught, so a standard kind of convergence statement, but maybe more sophisticated than what you've seen, and that's okay if you start at the right level for this course if this is the first time you've seen this exact statement. So I can make sure that I can have some sort of fence so that with a radius delta, so that as long as the variable t is close enough, is within delta of this fixed value t naught, the function g hat or g check t is close as a whole to the function g check t naught. And that means that no matter what value of tau you put in, the values of this function and the values of this function are less than epsilon. And that's a specified error tolerance. Okay, so what this says is that this sequence of, or this family of functions converges uniformly to g check t naught as t goes to t naught. So I don't want to make this too long. So it turns out that this is a fundamental concept in general, and it's a really good concept for what we're going to be working on. So what we're going to show is that that really is true for test functions, and that it's going to show that this is continuous. And we'll see how that works in the next video.